All right. So, like I was saying, we are actually going to continue from lecture 5. I know it says lecture 6 up there, but it literally is just a continuation of lecture 5. You should still have those notes. I posted the correct ones for you already up there, right? And just so you know, we do have an exam on Wednesday. It's scheduled for Wednesday, okay? And it's going to cover everything from day 1 till today, okay? But luckily today we're only talking about one thing, and there's only a couple examples on how to do it, and the rest of it you can do. The rest of it is the stuff that we've already done already before. Okay. Uh, so this will go by really fast because after we get done with this lecture, we need to talk about lab. Okay. So the next looks a little small to me. It's really weird. So last week when we were talking about velocity, right? A rate of change in speed and position. Okay. Well, today, and this will be the last thing we talk about for this exam, right? It will be acceleration. Okay, it will be acceleration. So, acceleration, right, is basically when you're at a certain speed and you speed up, right? But you can also decelerate too. You can go backwards and go slower, right? So that's what acceleration is. So the picture that you see up here is literally a guy on top of a building, and he's throwing or he's dropping a ball to the ground. And as he drops the ball to the ground, right? As he drops the ball to the ground, this ball is slowly, well, not slowly, but is surely picking up speed as it goes down, right? It's surely picking up speed as it goes down. So for this particular example here, the acceleration is being caused by gravity. Okay, the acceleration is being caused by gravity, and the ball, as it's falling down from the top of that building, right, is going in a well. First of all, let's just make note that the units for acceleration. Let me make sure I have my pen working. There we go. The units for acceleration, right, is meters per second squared. Okay, so notice how when you did the velocity, the units was meters per second, right? Well, the units for acceleration, though, is meters per second squared because as you, for example, this guy, as the ball's falling down, it's actually picking up speed, getting faster as it goes down, right? So it's no longer at a constant speed of meters per second. It actually is getting faster, and that's why the unit is meters per second squared. Okay, it's meters per second squared. So gravity, though, right? Gravity actually has an acceleration of, which you see part of it right there already because it's 9.8 meters per second. That's the velocity of the ball initially in the first second, right? But as it goes down, it gets faster and faster. The equation then becomes, not the equation, but the unit, not the unit, but the acceleration. Sorry, the acceleration becomes 9.8 meters per second squared, right? So that's how fast the acceleration is when you drop a ball down from a building, okay? And if you were to go through and do all this, these are literally just squared of the seconds, right? Because it gets faster and faster. If you're high enough, then there's this thing called terminal velocity where it just goes at it stops getting faster and it just goes at a constant speed until it hits something. So say you're like skydiving or something, right? If you're skydiving, you're doing the 9.8 meters per second squared for the first few seconds, right? And then you reach this point where you can't get any faster and you're just dropping like crazy, right? So how do you figure out acceleration, right? You figure out acceleration literally by having the average acceleration equal to the change in velocity over the change in time. Okay? Change in velocity over the change in time. Okay? When it comes to the variables, though, this is the variables right here. And don't worry, on the exam, I will provide you with all the formulas that you need so you can figure these out. But here we have constant acceleration. So an A with a line above it, right, is constant acceleration. And that equals the change in velocity over time, right? Which really is just the final velocity minus, I'm sorry, the final velocity minus the initial velocity divided by time, okay? So quite simply, you're going to be given things like how much time it took for something to fall, right? And you'll be given the what the velocity was at the beginning. Most commonly, it's zero. You're starting from at rest, right? And then you'll have a final velocity, and then you just plug it all in, and then you'll get the constant acceleration. The only difficult thing about these problems is going to be, as Gloria pointed out last week to me, is making sure you have your units the same, right? You got to make sure you have all your units the same. Okay, so we'll do an example right now, just so that we know how we're doing here. And no more, no worry, I'm not here to trick you. There are not going to be any trick questions. It will literally be straight up plug and play, plug and chug, except for when you have to figure out the same units, right? Convert to the same units. All right, so this is your very first question right there. Which of the following is the way that which of the following is a way velocity change can occur? Go and scan that stuff. If you can't get into it, I suppose you can just um, write it down on a piece of paper, because this is your attendance, and they're really hounding me about attendance today for some reason. So see, I figured since you guys scoot back a little bit now, you can see the. Oh, that's the problem. Dang it! Dang that faucet. Does anyone even use this faucet? That's weird. All right, let's see what everybody said. Let's see what everybody said. So this should be a pretty easy question because it's quite literally on the previous slide. It was quite literally on the previous slide. So hopefully everybody got this right. Forms. All my forms. Show more. Where's this one at? Can someone tell me what the name of this is at the top of this question? There should be, when you scan it, right? Actually, you know what? I'll just scan it. Just in time, scan. Yeah, NSC velocity. Oh, thank you very much. Oh, yeah, there it is. Okay. You doing it again there, Derek? What the heck is happening with this thing here? Okay. Everybody's logged in already. Good job. For most of you, right? 20 people said the answer is D, all the above. That is correct. The answer is D, all the above, because as you see from this very first thing I said right here, changes in velocity occur in three ways: increase in magnitude, decrease in magnitude, right? Speed up or slow down, and then change in direction of velocity, right? So good job there. Good job there. All right, so let's do our very first acceleration problem, right? Let's do our very first acceleration problem. So a race car is starting from rest and accelerates uniformly. So accelerate uniformly means that it's constant acceleration. Same thing, right? Okay. Um, and then along a straight track, that's good, right? Reaching a speed of 90 kilometers per hour in 7 seconds. Okay. So the thing to notice about this, the first thing to notice here is that um, it's starting at rest, okay? And when it starts at rest, that means that you're going to have the initial velocity equals 0, right? Because you're not moving at all yet, okay? You're not moving at all yet, okay? And then you know now to also hear from the problem that the v final, or the final velocity, is 90. That's weird. I wonder who's calling me right now. Don't they know I'm teaching? Anyway, um, the final velocity is right here, right? And that's 90 kilometers per hour. Okay, so you already have V0 and VF, right, from the equation from the previous slide already. Okay, so the problem that we have though is that, the problem we have though is that this unit here is 90 kilometers per hour. What is the unit for acceleration? Meters per second squared, right? So you have to get this to become meters per second squared, or meters per second, for it to work. So you're supposed to find the acceleration in meters per second, in meters per second squared, right? You're trying to end up with that. You're not going to end up with that with kilometers per hour, right? So you've got to convert the 90 kilometers per hour to meters per second, okay? So it's pretty easy. You can just say 90 kilometers per hour, right? And then cross that out there, right? So 1 kilometer per hour, oopsies, per hour, right? Is going to be, and you can figure this out later, right, if you need to, but I already did the math here. It's 0.0278 meters per second. Okay. So all you have to do now is cross those out right there and multiply these two to each other right here. Okay. So literally how I got this number right here, right? 0.278 meters per second is because I converted 1 kilometer per hour, right, to meters per second. Which we can go through and do that calculation later if you need to. So that gives us a grand total of 25 meters per second. Awesome, because now we have a unit that matches up with acceleration units. Okay. And so now we use our formula that I showed you just a second ago. A for acceleration equals the final velocity minus the initial velocity divided by t, right? Divided by t. This is pretty simple here, right? Because now you're just going to do 25 meters per second squared, or sorry, meters per second, minus 0, because it started at 0, right? We started at 0 at rest. And then what are we going to divide that by? Seconds, 7 seconds, right? 7.0 seconds. Okay, 7.0 seconds. So simply all you have to do now is just do 25 divided by 7. right? And 25 divided by 7 is, I have no idea, so I'm going to do it real quick. Okay. So what we get is 3.5714 dot dot dot, like a whole bunch of numbers, right? So what would be the correct significant figures for this? And what would be our correct answer? 2, I heard it. Someone said 2. So what's the correct answer? 3.6, exactly. The answer would be 3.6 meters per second squared, right? Because you're going to round up, since 7 here rounds up 5 to 6. Pretty simple, right? These are the kind of problems I'm going to give you on the test. I'll even give you the formula, right? I'll even give you the formula. The only thing, and I'll also give you the conversions too. So really, you'll just have to be able to find the correct formula, right? And find the correct conversion, and then do the math. I'll give you the formulas and I'll give you the conversions. You know, like one kilometer equals 1,000 meters, that kind of thing. That stuff. Okay, great. All right. So the next thing we have to do, though. So here, right over here, we solved for acceleration, right? Well, if you have an acceleration of time and a starting, you can also solve for what the final velocity is going to be, right? You can also solve for what the final velocity is going to be. Oops, I didn't mean to do that. Oops, there we go. So how do you solve for the final velocity? Well, we already know. We already have the formula, right? A equals Vf minus V0 over t, right? That's our velocity equation. Acceleration equation that we already have. And what we need to do is get Vf by itself, right? To solve for Vf, the final velocity, which is really simple. Super simple, right? Because oops, I didn't mean to do that. Sorry. There we go. Which is really simple because all you have to do is multiply both sides by t, right? That's the first step. Because then t cancels out, right? And you get this t here times that a. So now you get at equals, right? Final volume minus initial volume. Okay? Now how do you get Vf by itself? Exactly. Add V0 on both sides. So you add V0 over here, it turns that to 0. Add V0 over here, right? And now we have our new equation, which is, and I'm just going to switch it around real quick so that we can see it makes sense. Vf now equals V0 plus AT, right? AT. Now, do you want me to give you that equation too, or do you think you can figure it out from the first equation? We see how I feel that day, right? But it's really simple. But the point is, it's really simple, isn't it? Right? To get to VF, it's like literally like algebra, like high school algebra. Okay. So now we can solve for VF, or the final velocity. Okay, the final velocity. So let's do an example where we're solving for the final velocity. Okay. So if the car in the preceding example continues to accelerate, right? The car that we had before, right? In the example that we had before, continues to accelerate at the same rate of speed for 3 more seconds, what will be the magnitude of its velocity in meters per second at the end of this time, the final velocity? Okay. All right. So if you recall, right? If you recall, the previous example had him going how far? I forgot how many seconds he went. He went 7 seconds, right? He went 7 seconds, and he had a velocity there, right, of 3.6. So those are things you're going to need for the next problem. Not a velocity, sorry, an acceleration. So here it says 3 more seconds, right? So 3 more seconds plus 7 seconds equals what? A total of 10 seconds, right? A total of 10 seconds. Okay. You're looking for VF, of course. You're looking for VF. And you already know from the solve for VF, and you already know from the previous problem that the acceleration was 3.6 meters per second squared, right? So the equation we had before, right? And I'll just put the 10 seconds down here to make it easier to see. We have a total of 10 seconds, right? We have that information already, right? And then we already know that when he started this whole thing, he was at 0. So V0 is 0, right? He was at rest, right? So we have all those things already. Just so everybody knows, this is at rest when he started this whole endeavor. This guy driving this car, right? And then we have our equation that we used, we solved for a second ago, right? VF equals V0 plus AT. See, I tried to put a little curlicue thing at the bottom of my T's so we know the difference. That's pretty simple, right? Right? Because all you're doing here is you're putting V0 down here, right? You're putting your acceleration right there, and you put your time right there. Acceleration goes here, time goes there, and V0 is 0 at rest, right? So it becomes this. VF, or final velocity, is 0 plus 3.6 meters per second squared times 10 seconds, right? Times 10 seconds. That's pretty simple, right? Because literally it's literally just going to be 3.6 times 10, right? Which makes it 36, right? And we have here two significant figures. So, well, actually, yeah, we'll just say that there's a period right there, a dot there, so that we know that that's a significant figure. So two significant figures there and there. That means that we have 36. And then what is our unit going to be? Meters per second. Why is it meters per second? Because exactly this S here cancels out one of the S's over here, and now you're left with meters per second, right? Only one of these S's, not both of these S's, just one of them, okay? And that's how you solve for final velocity. It's that simple. It's that simple, okay? So like I said, the hardest part about these problems will be knowing what to look for, right? In the problem itself, because this one was kind of like, you know, 3 more seconds from the previous question, right? So you needed to add the 7 seconds from the previous questions to the 3 more to get the total time, right? And then you also had to get the acceleration from the last one too, and the at rest 0 V0 too. So this one didn't have any like conversions in it, right? But you had to pull information from a previous question, and that will happen on your exam. Okay. So those are the two things that might get a little bit tricky. Pulling information from the previous question. So you got to make sure your previous answer is correct, right? Because if you have the previous answer wrong, then it's going to make this one wrong, right? And then the other thing is the metric conversions, converting units to the appropriate units for acceleration, which is meter per second squared. Okay, any questions? It's pretty simple, pretty easy math, right? I'm sorry, say that again? Right. Okay, so acceleration is a vector quantity, and since velocity is excuse me, I'm sorry. Acceleration is a vector quantity, since velocity is a vector quantity, right? Because acceleration is can only happen with a velocity, right? So they're both vector quantities. And the only thing that is showing you here is the same thing that I showed you last time, right? Where you could go forward in velocity, right? And change your velocity going forward, okay? Or you can go backwards too. And the difference is that when you're going forward in velocity and your speed increases, right? Then you have an acceleration. But if you're going backwards and your speed decreases, not backwards, but like if you're slowing down, right? Then you have a deacceleration, which is pretty self-explanatory, right? You're slowing down, you're deaccelerating. That means your velocity is getting slower, right? But if you're speeding up, then you're accelerating. And so the thing you just need to know is that acceleration is always going to be a plus sign, and the deceleration will always be a negative sign. Okay, pretty simple stuff. And then lastly, this is the last slide for today, right? This is the last slide for today. This is just explaining what we had before with that guy falling. Not falling. He wasn't falling. The ball was falling, right? But if the guy was falling, it'd be the same thing, right? Where gravity equals 9.8 meters per second squared, right? So G equals 9.8 meters per second squared, right? And you'll see later on that when we do force and motion, that there's an equation from Newton's laws called F equals ma, right? Force equals mass times acceleration. But when something is falling, it's actually force equals mg, because it's also an acceleration, right? But we'll talk about we'll talk about that more in detail after the exam. But the thing I just want you to notice here is that the increase in velocity, right, when you're talking about gravity, it's linear. It goes straight. It absolutely goes straight. Okay. There's no curve to it. It's absolutely straight. And that actually ends our lecture. And this is how you know that this is a continuation from last week. It says you have a quiz in the thing today. Okay.